Hi, everybody. Welcome to SIGCOMM 2021 and the preview session on wide area networks and beyond. My name is Banaz Arzani, and I'll guide you through what you can expect in this session. So I don't know about you guys, but when I was an undergrad, this is what I thought a network looked like: a collection of nodes that communicate with each other through packets. Incidentally, this is the ARPANET in December 1969. Well, by the time I was taking my first networking class, the internet was actually much, much larger than a simple network with over 1 million nodes. And today, when we look at the internet, we also have data centers that are almost just as big as the internet was in 2004. And wide area networks are the backbone of the internet and what connects these data centers together. And what we have are public wide area networks that are operated by multitudes of companies, which each manage a number of autonomous systems, or ASs, which are smaller networks that are stitched together to form the internet at large. And we have private WANs that are managed typically by single organizations and connect the data centers of that organization together. These are managed, for example, by companies like Microsoft, like Google, like AWS. And when we look at public WANs, they serve a variety of different traffic types. For example, video traffic, which today is the majority of the traffic served over the internet, or voice over IP traffic, or web traffic. And they are designed to keep uptimes high. As users of these networks over the years, we've started to expect higher and higher availability from them. An example that I like to share in a lot of my talks is one where a couple of years ago, when Facebook went down, people started to call 911, and the police department had to issue a tweet to say that we had nothing to do with that outage. That's the level of uptimes we've come to expect from our service providers, and which is why that ISPs have started to compete to have higher and higher uptimes and to have more resilience towards failures so that they can keep and maintain their customer base. For the same reason, wide area networks that are public are typically designed to budget for capacity to handle failures if and when they happen. And finally, because they're managed by distributed networks of autonomous systems that are stitched together and are managed by individual companies, they typically use distributed routing protocols to communicate with each other and to connect the internet as a whole, protocols such as BGP. On the flip side of that, private WANs serve rate elastic traffic, and because they typically tend to be expensive to provision, they push for high utilization. And they focus on traffic utility as their main objective. And again, as we mentioned earlier, because they are managed by individual organizations, we have the luxury of actually using centralized controllers to optimize how traffic moves through them. Algorithms such as SWAN and V4 are examples of what operators do in order to route traffic through these networks in a way that serves a number of different objectives and can satisfy a number of different objectives. Now let's go back to the public WAN scenario. In addition to internet service providers that manage these individual autonomous systems, there's other players that are involved in these networks. Players such as content providers. These are those companies that produce the information that we, the users, consume over the internet. Companies such as Facebook or Netflix are examples of such content providers. We also have CDNs, content delivery networks, and caches that serve this content to us. An example of a CDN, which many of you might have heard about, is Akamai. Or on the other hand of that is Netflix's Open Connect, which is caches that Netflix puts inside ISPs so that they can put their content closer to us, the users, and serve it to us at lower latency. We also have internet exchange points, which are places where different providers peer with each other to be able to exchange traffic. Now, on the other side of this, as we talked about earlier, we have private wide area networks that are managed by individual companies. These can be much more optimized for performance and also for efficiency and cost, which is why a lot of the times during provisioning, operators think through how much traffic these networks need to be able to handle and try to provision them at a reasonable cost. And at runtime, they run sophisticated traffic engineering algorithms with various different objectives, such as failure resilience or achieving high utilization and so on, to be able to get the maximum benefit out of their networks. So now let's look at what research has been done on public WANs. So when we look at public wide area networks, a lot of work has been done just on measurement and trying to understand what these networks look like. Work by people you might know of, such as Philippa Gill or Ethan Katz, that look at, for example, what does routing in these networks look like? What are the security properties of these networks and so on? There was work on network economics and policy to try to understand, for example, what is the impact of network neutrality, or to understand why protocols such as BGP-SEC weren't adopted as fast as people expected, or IPv6 as another example. There's work on the security of these networks, how to prevent DDoS attacks and prevent other types of attacks that might be going on. And finally, and what you're going to be hearing about most in this session, routing and traffic engineering. For example, the fundamental work of Forts and Thurop that looked at how do you assign link weights such that routing converges to an optimal solution. So when we look at the research in the public WAN space in SIGCOMM 2021, we have this one paper that looks at how hypergiants have moved off nets. Remember earlier we talked about Netflix's Open Connect? So Netflix is a content provider who's now putting caches inside internet service providers' networks to move closer to the user and to create better performing content delivery networks. And what this work looks at is, as academics, how can we discover how these hypergiants are moving closer to the users and how they're putting their presence within the different ISPs and what their strategies look like. And they point out that prior work in this space is inaccurate at best. They use DNS queries, for example, to discover hypergiant presence, or they're tied to a particular hypergiant's operational semantics. And because of that, they tend to be fragile and not necessarily accurate. The authors propose a new measurement system based on TLS certificates to uncover a hypergiant's off-net presences and expansions. I highly encourage you to listen to that talk and learn more about this work. Now, next, we're going to talk about what research is being done on private WANs. So similar to what we talked about on the public WAN space, there's a lot of measurement work that looks at the properties of these networks and the properties of the optical topologies that they tend to operate. There's work on failure recovery and reliability. Some work in this space include FFC, TE-AVAR, that look at how do you do traffic engineering to have failure resiliency. There's work on the securities of these networks. And then finally, there's work on routing and traffic engineering, work such as NC flows, such as SWAN and B4, which we talked about earlier, that look at how do you route traffic through these networks so that they're operated efficiently. So what can you expect from the private WAN session in SIGCOMM 2021? So mostly this session is going to be focused on traffic engineering and provisioning for traffic that's going to be going through these wide area networks. So before we dive into the papers themselves, let's talk a little bit about what traffic engineering is so you can kind of figure out what you can expect. So when we look at traffic engineering in private WANs, we're talking about centralized controllers, which have the entire information about what the topology looks like and about how much demand to expect, or a rough idea of which sources want to talk to which destinations. And they tend to be formulated as linear optimization problems, and they often have to be integer linear optimization problems. They have objectives such as to minimize the cost of sending traffic through these networks, or maximizing the utilities of these networks, or ensuring failure resilience. So for example, if you look at TE-AVAR or FFC, their objective is mostly to have failure resilience. On the other hand, if you look at something like NC flow, its objective is to serve maximum utilization or max flow to satisfy most of the demand that they can through the network. And they often have constraints. So some of the constraints you need to satisfy when you're doing traffic engineering is you need to ensure that you don't serve more traffic that actually exists, right? So you have to have flow conservation. You have to make sure that you don't exceed the available capacity on any given link. And depending on what the authors are doing and what the work is trying to optimize, there might be other constraints as well. So what can you expect from this session? So first, we're going to see a paper on cost-effective capacity provisioning with SHU-FLY. And what SHU-FLY does is it observes that the optical to electrical to optical, or OEO conversions, that we do in these wide area networks are typically not always necessary. And so they propose bypassing or bypass-enabled topologies that allow shortcuts to avoid these OEO conversions when possible. And by doing that, they reduce the hardware costs when provisioning these private wide area networks. The challenge that TrueFly addresses is how to allow for such shortcuts while maintaining a failure-resilient network that can continue to serve ongoing traffic demands. Next, we're going to have a paper from Facebook on capacity-efficient and uncertainty-resilient backbone network planning with hose. What the authors observe is that the pipe model that people typically use for forecasting worst-case traffic demands, this is a model that basically looks at the sum of the maximum demands between source and destination pairs and uses that to understand how much traffic the network needs to be provisioned for. And they observe that that's not probably the best idea. Instead of doing that, they propose using the hose model, which instead looks at the maximum of the sum of demands between source destination pairs. Now, if you look at the convexity concavity properties, you can kind of understand why this makes sense. And use this hose model instead for provisioning Facebook's private plan. Next, we have Arrow, which is a restoration-aware traffic engineering solution. And what the authors observe is that fiber cuts typically result in reduced capacity in private LANs. And what they think we can do is to revive the lost capacity through reconfiguring the wavelengths from cut fibers into healthy ones. And they do so by doing a joint optimization across both the optical layer and the IP layer, and do restoration-aware traffic engineering. And with that, I invite you to listen to this session and to enjoy all of the papers that the authors have to present. Thank you. Was I not?